In this lecture, we're going to review some very important statistics that will quantify measures of variability. And variability measures are those numbers that attempts to describe how scores and the magnitude of how those scores differ from each other. And there are three aspects to variability measures. The first is that variability measures indicate the consistency of scores. The greater the variability among a set of scores, the lower the consistency is considered. Uh, Variability measures also function to describe the accuracy of how these three central tendency measures characterizes a set of data. And essentially, the greater the variability in the data or the values of the scores within a distribution, the less accurate the mean accurately or the mean characterizes that distribution. And the third aspect of variability measures is that it measures how spread out the outcome scores are for a sample or a population. The most basic way to quantify variability is what's called the range. And the range is just simply the distance between the two most extreme scores in a distribution. And this communicates how fully spread out the data are. And what we see here is that the range is just simply calculated as the single highest score in a group of scores subtract the single lowest score. This is considered to be the most crude measure of variability, but is the one that is often used for nominal and ordinal data. It is also used for interval and ratio data as well. And one limitation of the range is that although it captures the full distance between the two extreme scores, it does not provide any information as to how the scores are distributed between the maximum and the minimum. And so that leads to another development called a deviation score. And the deviation score is typically used for interval or ratio data that are best characterized along a continuum. And this attempts to measure the difference, to describe the differences between the scores in a distribution, and is based on the normal distribution with respect to the mean. We begin by defining what a score deviation is. And the score deviation refers to the distance between a single score and the sample mean. So if a sample has 30 scores, there will be 30 deviation scores, as there is only one sample mean. And the magnitude of that individual score's deviation from the sample mean is just simply referred to as an error. And the error does not indicate that any sort of mistake was made. It is the term used to describe that deviation of scores around the average. And the deviation score is just simply the difference between a single score in a distribution, subtract the average of the scores in that distribution. So to compute each person's deviation score, the order has to be maintained. And a single person's deviation score can take on a positive or negative value depending upon where that person's score lies with respect to the average of the group. One of the problems in calculating deviation scores by themselves is that if we add up all the deviation scores of all, for example, 30 research participants in a sample, that will all equal to 0, as some of the scores will be positive and the other scores will be negative, And if we add up all the deviation scores, it will sum to 0. One way to begin to come up with a manner to quantify deviation potentially is by calculating an average deviation. And an average deviation is a single number that provides that overall picture of how the average score deviates from the average value. And so what we see here, to compute an average deviation, we just simply sum up all the deviation scores and divide it by the total number of scores, where n is the total number of participants. The problem with this approach is that the average deviation, a single value that captures how spread out the scores are around the average, will always sum to 0 because approximately half the scores will be positive, the other half approximately will be negative, and when we add up all the positives and all the negatives, it will equal to 0 because scores will be generally balanced around the average, particularly if those scores do fit a normal distribution. So to deal with the problem of the zero-sum problem related to the deviation calculation, two different approaches were proposed many years ago. Sir Arthur Eddington, who was an astrophysicist and mathematician, developed and proposed that each deviation score, so each person's difference from the group average, would just be taken as the absolute value. So if a single person's deviation was, for example, negative 15, the average deviation, or rather the absolute deviation, would just be a score of 15. Another scientist by the name of Sir Ronald Fisher, who was a statistician and biologist, proposed a different method in which a single person's deviation score would simply be squared. So by squaring the deviation for each person would have the same effect as taking the absolute value for each person's deviation, in that the negative sign would be eliminated, and as such, the zero-sum problem is resolved. However, the development of the field of inferential statistics tended to focus on the approach of Sir Ronald Fisher. So the squared deviation became the superior approach to use because it was found mathematically to be a more efficient way to deal with the zero-sum problem than the absolute deviation approach. And it tended to produce a smaller variability value under ideal conditions. The squared deviation approach was found to be easier to manipulate and to work with algebraically in subsequent steps, and as such, inferential statistics moving forward were developed and based upon the squared deviation method of addressing the zero-sum problem. And this led to the calculation of what's called the standard deviation. So the S squared of a sample of data is referred to as the variance, where we see that each score that is taken as the difference from the group average is squared, and then the next squared deviation is added, and that is then added to the next squared deviation, so on and so forth. So if this sample had a total sample size of 30 research participants, there would be 30 squared deviation terms to add up. And then that is divided by n minus 1, where n minus 1 is referred to as the degrees of freedom. The equation on the right-hand side is the square root of the variance equation that we see over here on the left-hand side, and Sx is termed the standard deviation. And in terms of quantifying and describing descriptive statistics, the standard deviation is the variable, or rather the statistic, that is used to provide a single value that captures how spread out data are in a particular distribution. And these equations do not include n, but n minus 1. And so if your sample size includes 20 research participants, only 19 of the samples would be free to vary from the population mean. And so the summation of the squared deviation terms would be divided by n minus 1 and not n, as essentially an average of the deviation scores of all of the research participants. So this ends this lecture, this part of our Unit 6 on Unit 6 component on observational research.